Action. All right, everybody. Welcome back. Funny story. So I've been a dedicated Windows user pretty much all of my life. I wrote my first base computer program, though, on a Mac. And this year I ran into some issues with Windows. And so I decided to switch to Mac for everything. I never had a problem with it connecting when Windows. Like I always felt like Windows was a problem before Mac was. And then today, try to connect, and it turns out the Mac is the problem. So I'm switching back. Just kidding. So how's it going? Good. What do you remember from last time we met? Well, it was a quick class, I know. It's funny, this room, the density of student per foot on this side is high, and then everybody over there is kind of like spread out. It's like the suburbs, right? This is downtown, and the suburbs over here. It's pretty awesome. So, a little bit about me. I got back at like 1:30 last night in the morning. So, but I'm dedicated to bringing you a lecture. And here I am, and I am impervious to the effects of jet lag. That's what I've learned. So let's go. I was just in Singapore giving workshops to their Ministry of Education and Educational Assessment people, and I get the great joy of being able to teach in Singapore on like Monday and then on Wednesday in Kansas. So it's a first for me. I've never been to Asia. Never been anywhere over there. It was a good trip, although very long. So, in the meantime, I left you with some R stuff. Did anyone try the R stuff? Little do you know that I actually have the ability to see who hits my website and when. Not who, but when my website gets hit for stuff. And I noticed in the last couple days the R stuff picked up. So it's okay if you haven't really tried it. The main thing I'm really going to tell you is that I switched, you saw my email yesterday, I switched the homework so that we have 6 instead of 7, and part of that is because the automated homework system I use is still under development, so it's still coming along, but it should be ready for next week. So you'll have a homework assigned next Wednesday. It'll be on this material, so if you haven't started on R yet, you still have a week, although the assignment will be due 2 weeks later, so nothing like taking our time, right? But each assignment then, it works out to still the 84 points of homework that we talked about before. Just each assignment will be worth 14 points instead of some variable amount between, however. So nothing else changes according to that. Do you have any questions for me before we begin? It's quiet. It's good to see all of you. Let's start. Today's class, we're going to take the linear models where we left off 2 weeks ago and dive a little bit deeper into them. Let's talk a little bit about why this matters in terms of multivariate. So I always like to tell you why as we go along. Linear models, as you saw before, we get all of our answers from in terms of regression, ANOVA, and COVA, MANCOVA, all that fun stuff. And in particular, to do multivariate analyses with linear models, what we will end up needing to do is a bunch of interaction effects. In fact, a multivariate model for data, we're going to have to, after we get through path analysis, we're going to have to switch over to regular linear model software, and we'll have multiple dependent variables. But they won't look like multiple dependent variables. It'll be one big long column of data. And through a series of interactions and predictors and so forth, we'll be able to arrive at what we need from a multivariate analysis in that framework. Now you might say, wait a minute, when we get to path analysis, you might think, path analysis is so amazing, there's pictures and it's fairly easy to specify, why would I ever need anything else? And that's because not a lot of path analysis software does multi-level models, which are things that you'll need to do, or does estimation with residual maximum likelihood, which is another part that we use for a lot of mixed models that we do these days. So it may be the case in a few years you may have to worry less about that, but that's where interactions show up, and because interactions are like describing interactions is the bread and butter of everything we do in statistics. So I was over in Singapore, as I mentioned, and it's 14 hours ahead of us. So every time, daytime there is like nighttime here and vice versa. And so I was getting, trying to catch up on political coverage of Iowa's caucus is coming up. And they're talking about weather interacting with it. And the person on CNN International, this weather person, was saying that it's interesting that for every 1 inch snow above the average, then the turnout for Republicans is higher by this number of percentage. I'm like, oh, hey, that's an interaction right there. He is describing an interaction, the interaction effect of snow on voter turnout on voting days. And so it's very interesting comparatively. So we're going to talk about that very same thing. In fact, he was talking about for every 1 inch of snow more than the average, that is not only an interaction, that's a centering issue. Remember last time we talked about subtracting off a constant from one of our predictors? Well, in interactions are based on where the 0 point is of the other predictors, so he had centered on it. So you'll see interactions show up quite a bit. A lot of times the people in broadcast journalism, if they talk about them, I don't think they talk about them in the way that he did, and he did it right. And so I was very impressed. So way to go, CNN International. Not that I was curious, not to try to talk about politics. It's how you take a statistics class and make it like you take something that's boring and make everybody already angry even more angry. So talk about politics. If I show up with my Donald Trump shirt, no, I'm just kidding. Just kidding. I can't participate in the early season elections because I hate every party, and that means I'm not registered as an independent, which is the party. I am undeclared. Literally, that is how I have to do it. So I can't take part in the primaries because I don't like any of the parties. So if you ask me what I think we should fire them all. I'm for the anarchy party. No, I'm just kidding. All right, so we're going to talk about more centering and coding of predictors. And I know last time I was flying through the slides going too quick. So this is our chance to catch up a little bit. I'm telling you, next week, because again, today I feel very, still recovering from the trip. So next week I will make sure I learn all of your names. All right, keep putting that off. Good at procrastinating. So I will go through that, start that next week. We'll also interpret parameters for the model for the means. We mentioned the model for the means last week. That is the part of the model that does all the prediction, or as we would call it in every stat class up to this part, the model, right? The regression analysis, the thing where you put the predictive variables. Then we'll get into describing main effects within interactions. And so whenever you see a regression model or an analysis of variance, whenever you put an interaction in, it modifies or moderates all of the main effects underneath it that involve in those variables. So we have to describe how those happen. And I'll give you an example, regression versus ANOVA. Although that makes it sound very competitive. Right? It's not. It's all the same thing. It's just more a distinction that gets made if we were using other software packages. And as we go along, I do want to show you, if you have downloaded R and RStudio and are on your laptops with it, the R file from this week, if you put it in the same folder as the R data and pull it up in RStudio, you can follow along as well. The way RStudio works, it pops up here, and what you should be able to see, I actually have all of the data from before. I'm going to clear it. You have a bunch of lines. Up at the top left is our code, so that's our syntax for everything. And to make RStudio read in the data, the first thing you have to do is to make sure that you're in the right folder where the data happens to be. So to figure out where R thinks the folder is, you can go down to the bottom left here and type get WD, or for get working directory, and it will tell you where R thinks it is right now. So it's in this folder on my computer, C, Dropbox, yeah. So if you have the data in that folder, then this line that you see here on line 12, data 01, is a read.csv that reads in the data and puts it into data, a thing called data 01, an object. So to run a line in RStudio, you highlight it and hit run. Although I hate having to use the mouse, so what I typically do is hit Control and Enter, and that will do the same thing. It will run that So now, if you ran that, you'll see that data 01 shows up over on the top right. That right there is where all the R is something called object-oriented. So every type of entity that you created, it has its own class or its own type, and each type of thing has its own set of structure to it. This is a data frame. So if we click it, you'll see there is our data. A data frame is kind of the closest equivalent to how you'd see data in SPSS or otherwise. And so I try to work with them exclusively in this class. If you run into issues in R or RStudio, a lot of times those issues happen to come from the objects not being the right type to do the type of analysis you want it to be. But for most of what we'll do, with the exception of matrix algebra, we'll use data frames. And in matrix algebra, we have to switch the object from data frame to matrix, but there's a little command to do that. So there's your data. The other thing about R that I'd like to tell you is that R runs, it's like, how do I want to say it? R is like the App Store. Yeah. Those of you who use Apple. It runs with a series of what are called packages. So R has its own base set of statistics that it does, but then to do more than that, people can write their own script and put them into a package, and anyone can download the package. And so in RStudio, under the Tools menu, there is an Install Packages link. And actually, I can zoom in if you want to see this. So you go to Tools, Install Packages, and then it pops up a box right here where you can actually type in the name of the package you'd like to see. So oftentimes if you're using R or you're looking at people's papers that talk about analyses with R, the package, they'll talk about this package they used. You can find it, you can type it in here, like the one we're using today is something called multcomp. So you can type multcomp and you click it, and what it will do if you install it is it'll run some syntax down here, download it from the internet. So you have to be connected to the internet, by the way. And then once it's installed, eventually, it'll tell you where it's downloaded it to. All the syntax that you see right here in between these two sets of lines, line 14 through 19, does the steps that it just did, if it's not been installed already. So you don't have to, the syntax at the top of my lecture files, all these things right here, this is built in, it's all you have to do. You just have to run it. It'll do it automatically. Like so, this first part, just to describe what it does, I ask it, do you have the package multcomp already installed on the computer somewhere? So require multcomp goes and says, hey, is it there? And then has package is either true or false. So for me, it should be true if I run that line. Whoops. So it says true. So if that's the case, to load up a package, you have to type library in the name of the package. So it'll skip installing it and then runs it. So big picture for this for you here. You don't have to know this code. All of this will be given to you ahead of time, but just to sort of give you the whereabouts of what's doing what in R, that is how this syntax is built. Any questions so far? By the way, I'm recording this, so you'll be able to go back and re-watch this with my voice over it. You won't see a picture of me, thankfully. Yes, sir?
How did you pull up that box where you could enter the package you wanted?
If you go to the very top under the Tools menu, there is an Install Packages option, and the box will pop up. Generally speaking, that is a good way of finding the packages you want, although you have to know their name, type it in. For all of our syntax in class, including the syntax that we'll use on the homeworks, I will give you a file that essentially has this first bit to it that'll automate that whole process so long as you're online. The other issue, and this actually came up in Singapore because I used R to teach there too, if your laptop or desktop or whatever computer you're using doesn't give you permission to write to certain places, then it can't download the package and save it on the computer, and that causes it to have problems. So if that happens for you, let me know, and we can put a workaround in it for you, or it kind of has to be tailored to your computer and situation, but I'm happy to help. If you can run all this code while you're connected to the internet and you see it install things and it doesn't give you any red over here, you're good. Okay? And it should be the case that when you're connected to the internet and you're on a computer that gives you permission to write files to wherever, then you should be able to download the data and this R file, put them in the same folder, and just run them to begin, and you'll be able to replicate everything that happens in our analysis. Okay. Questions? Yes?
Well, I'm not able to save the data and put it into a file. Just delete.
Does it just show you the actual commas delimited
I
file?
just clicked the link in your website for the.
Okay.
And then it just opened up in another window.
In the browser itself.
Right.
If you go back to the link, right click it, there should be, which browser are you using, by the way?
Firefox.
Firefox. I think you should be able, there should be a save as option.
Save link as.
Save link as, that might do it. That should do it. Then it should pop up, it should end up with a CSV file. Yeah, it should end with a CSV itself. Anyone else have that problem? Let me see, real quick. Yeah, that should be fine. Small files. And make sure this is not CSV. There you go. That should do it. You're welcome. All right. Other questions? So my goal is to show you snippets of R as we go along, but if you'd like, pardon me, if you can't get it to work, then on the website, oops, that's not where I'm going, this one. Come on now. Go to the website and we have, I just noticed it says 2014. How terrible is that? On the page that has the post itself, I should pay for a better server. Bless you. There is an R Markdown link. That link should show you the R, what happens when I ran R. So you should be able to see all the output you get. So if you're not able to run this during class and you want to flip back and forth, you can go over to the website and get that output itself. Okay? So a little bit of survival guide for this. How many of you tried R while I was gone for the first time? Awesome. How was it? Nobody's going to say loved it. How many of you love R? Yeah. Right over here. Why do you love R? Once you get to know it, it's easy. I don't think. Did you find easier than other things? I was going to say it was never easy for me to learn. I do programming, but once you see it, once you get to know it, it certainly has a lot of good functions to it. Anything else? Anybody else you want to add? For those of you who are beginners, do you have any words of advice for beginners? I'm trying to give you peer support for those of you starting. Power through it. Yeah. And again, don't hesitate to ask if you have problems. Yes.
What's the difference between the colors?
In RStudio, if you see green, this darker shade of green, that is a comment. So that is not in every line that ends with, that starts with a pound symbol or hashtag, makes it so that whenever you run that line of syntax, R doesn't interpret anything. All right. So if I go up here to automating and I submit it, and you'll see it submit down here, it didn't do anything. It's just a comment. Anything that you see in a lighter shade of green is what R will interpret as a string or a character. So in this case, it's looking for a file, and it's going to use this character string, the name of the file, to go and open the file itself. In the case of blue, those are keywords that are important to R. Now, not everything gets turned into blue in RStudio, but kind of the key word here, true. True or false in R are a type of logical, it's a type of object, it's a logical variable. And if you type true all in capitals, you'll see that happens. You'll see over here this variable itself's value is true. False is another one. But then, yeah, here's false right here. But then require, if, library, those all get turned blue. Those are kind of reserved commands in R. I think the word for to do a loop also does. But occasionally, but you'll see for most of RStudio, not a lot of things are blue. Only a few things are. So if you see blue, it's kind of like a reserved key term in R, I think. Anybody else? It may mean, it depends on the machine or whatever else, but if you don't see any, don't worry just yet. As you go later on, like there's big sections down here that doesn't have any color, and somewhere it highlights the color and so forth. The other thing you'll learn about R is that there's usually multiple ways of doing things. So if you're looking at my syntax and saying, why did I do it that way? Or better yet, you have a way of doing it yourself, or you read someone else's website that did it differently, that's fine. That's actually probably going to be expected. So what you'll end up doing or seeing as you go along may differ if you try to replicate this from what I've done. But this is just my way of using R, that's all. So it doesn't have to be my way. And not only that, as you get better at R, maybe the folks who use R and love R, the R lovers downtown over here, they you'll learn that the way you structure your syntax differs as you go along. So like right here, this by command, I would have never used like 2 years ago, but this is a command that runs an analysis. In fact, it takes the standard deviation and divides it by n, or gives me the standard error of the mean, but it does it by group right here. Right? So that's a lumping of everything together. So what you'll get in R is varying levels of embedded stuff that doesn't make any sense. If you have questions about that, please ask. My goal is to make the parts of the analysis that you'll need to do as obvious as possible, and not make them all embedded like that. Like, I won't give you a homework that says do this. Right, this is more just give me the numbers I want as fast as I can do. For doing homework, I'll point out the functions that are most important. In fact, the snippets of R syntax I put into my slides, those are the ones that are really the ones to key on. Okay? Because if you're like me, the first time I saw R, I didn't. I used the regular R window that makes it really hard to like put syntax and command line together. I didn't see any of this, and it was like over my head. So I get it. If you've never used it before, just hang in there. I'll make it work. And I will tell you, it's not easy. Unlike once you get to the part like Megan over here where you're proficient at it, it feels like it's easy comparatively. Like I feel like, yes, I used SAS exclusively up until I used R almost, and so now going back to SAS, it seems a lot clunkier. So comparatively, but at first it's not easy. Okay, other questions?
What if so yours is like an Excel data file on the side?
Yep. Mm-hmm.
Whereas mine has like a list of things.
Ah, does it look like that?
It
No.
looks more like that, but not exactly.
Well, let me look at that during the break, and I'll help you with that. Okay. Generally speaking, it depends on what R read when it reads it in. It tries to make it into a data frame that may not always get there. But if it isn't, I'll see what happened. Cause the difference from it. I've also found in teaching from R, I'm learning about differences in machines and computers and so forth. And so the last time I taught multivariate from it seems like there were a few catches about how it read in the data, so it might be one of the things that you see there too. So it'll help me work through it a little bit better. Anybody else? Okay. Let's get back to the joy of statistics. It's fun, right? How many of you think statistics is fun? So we still have a high correlation, but it's not with the first group, but yeah, not many of you, huh? Is there anything I can do to make statistics more fun for you? For those of you who don't think it's fun. Not yet.
Show us graphs. That's what Billy does.
Graphs?
Show off all the colors.
Oh, I don't care about that. R does great graphs, right? But graphs are only so. Do the statistics first, and then make the graph. That's what I say. Anyway, I'm messing around. Are you trying to tell me I should be more like Billy?
Not.
No, I think that's.
You simply ask for suggestions.
Here's a nice picture, right? It's not a graph. Table. Okay, so we're going to start by looking at an effect of a new instruction method. So I'm going to code up a variable. It's called new. I'm going to dummy code it, a 0 and a 1. And I like to make my dummy coded variables labeled what the 1 happens to be, right? So this is a new. The variable name is new, and that means if you see a 1 there, that's the new way of teaching. If you see a 0 there, that means it's the old way of teaching. On test performance, percent correct in this case, in college freshmen versus seniors. So for instance, this is another categorical variable. I've got to code it. I call it senior. You would expect a 1 to mean senior, a 0 to mean a freshman, right? And I'm saying that, making a point of that, because the point of this exercise is what happens when we make things 0 and 1. Now that sounds pretty ridiculous, but that's kind of the bulk of a lot of interpretation is what did I call that when I put it into my analysis. Interesting aside, you can label it whatever you want. I don't care. My advisor in graduate school told me a great story about dummy coding variables. I'm sure some of you have heard this before, but he was working with a Native American tribe in Wisconsin, and he had an indicator variable for whether or not a person was a Native American. And he used a lot of the ways that he coded things would be to indicate they were dummy coded with the letters DUM. And so he had coded it dumb, and he used the word Indian to describe the Native Americans. Now that was bad enough, but then he went and didn't change the label in a presentation to the tribe. So if you're going to put dumb on anything, probably don't display dumb Indian in front of a bunch of Native Americans. A terrible idea. Dumb anything is a terrible idea. So labeling a lot of the stuff that you're going to see about interactions is we have to keep track of. There's a lot of things to keep track of. So any way we can make a shortcut, such as putting a label that represents a variable or so forth in it, it makes the accountancy that much more straightforward. So we have 25 people per group, and our linear model, remember a linear model, that's ANOVA and regression put together, says a test score for a group or for a person is equal to a function of an intercept, a main effect for being a senior, a main effect for being in the new group, and some two-way interaction between senior and new. And at the end of all of this, we have error. So as we go forward, we're going to describe all of these terms again. But looking at this box, what we'll see here is that the intercept, each of these parameters has a very specific meaning in each of these cells. Right? So here in the orange area, we have the cell means, or the average for each of these groups. So people who were freshmen and using the old method had a cell mean of 80.2. People who were seniors using the new teaching method had 87 for their mean. The bits and pieces that show up around it represent the standard deviation in each group. So if I just looked at that group's data, what the standard deviation of their scores would be, and then the standard error of the mean, which is standard deviation divided by n, or square root of n. So you can see how each of those differs. In the bottom of the table, we call these marginal numbers that we saw before. So this represents the mean of the group that you see all the way on the other side. So the mean old method, regardless of whether you're a senior or a freshman, was 81.28. And the mean for the new method was 87.52. Again, regardless of whether you were a freshman or a senior. Similarly, marginal means for freshmen was 84.08, regardless of whether you got the new method or the old method. And same thing with seniors. The marginal mean was 84.72, regardless of which method you received. we're teaching. So marginal means sort of aggregated over, or in this case, you can literally see the meaning. It's the margin of the table, right? Whereas conditional is the center, right? This mean is conditional on being a senior and being in the old method. Cool? This last thing, this is the grand mean, which makes it sound so much better than it really is. Right? It's the mean of all the means, or mean of all the data altogether. Right? Okay. So our focus today is on the section of that linear model from the previous slide that does the predictions. This is what we call the model for the means. And in the prediction, there you'll see all of our independent variables, x and z in this case, just generically, and their regression coefficients that go with them. This portion provides each person's predicted or expected outcome. And that's the key. That's why it's called the model for the means. The predicted outcome is true for that person, but really it's true for all types of people that have the same predictors, right? And so that's why we call it a mean, or another synonym for mean in statistics is expectation. So the marginal mean, or the model that we're using for the mean, provides a prediction for each person, but moreover, it's thinking about it as if we observed a lot of people like that one person with that one pattern of x and z and so forth. The parameters, so here the parameters are beta 0, beta 1, beta 2, and beta 3. Those are all the numbers that come out of the software package itself. Here we call them fixed effects. Fixed effects. Yes, I said that right. Trying. I may be slightly wrong about being impervious to jet lag. We'll find out. See how well I'm here cognitively by the end of the lecture, right? These things are called fixed effects because we don't put any assumptions about distributions to them. They're just numbers, right? We're trying to estimate the best value for them. As opposed to a fixed effect, that error term actually has a distribution. We say error follows a normal distribution. That's the kind of the distinction we use. So these fixed effects have a distribution and don't have a distribution. We're not giving them a distribution, but simply by observing them and observing a lot of them, we can kind of infer what was called a sampling distribution from them, in that if we were to do this same type of study on the same size of sample over and over again, kind of what their trend values would be. So here the number of fixed effects that we see later on will show up in formulas as a k. So here there are 4 fixed effects. Okay, so that's the prediction, and we've got data equals prediction plus how far off the prediction happened to be, right? So once we have data, once we put the data into a stat package like R, in this case it's the function called LM for linear model, we get a prediction for each person. To recover the data fully, though, that is, we have to add to it how far off we are, right? And so that's what error, or the residual part, happens to be. We call that the model for the variance, and it's sort of a silly model. There is no model for the variance. It's just a variance. There's only one of them. I think I mentioned this last time. We think there's only one in our model for any person themselves, but if we looked at each person and we looked at the distribution of these e's, right, we would assume, what we're going to do is make an assumption about that. We're going to assume that error follows a normal distribution, that there's a zero mean, and that there is one single variance that describes all the errors themselves, or that they are homoscedastic, homogeneous. That's right. If you use the word homoscedastic in language this week, tell me about it. Better yet, if you tweet about it and put me in the tweet, I might find a way to get you some extra credit. Actually, check that. To make the extra credit, you've got to use the word heteroscedastic on Twitter.
That's not fair. What if we don't use Twitter?
Doesn't apply. It's extra credit. Doesn't matter. It's free. If you don't use Twitter, you can put it on a bumper sticker and put it on your car. How does that sound? And take a picture and send it to me. Then I'll tweet your picture for you. Anyway, basically what we're saying about homoscedastic is that we're assuming everybody has the same variance, right? The variance of error is the same regardless of what your predictors are. And if you look at it, look at this here, the variance of error, although we don't see variance of error here, what we should see sort of is the homogeneity of variance in each cell. That's really what we're after. And it varies a little bit. But the model that we're going to use, that we're going to apply to this, is going to assume all of those be the same variance for all of it. Now, it's called the model for the variance because when we get into multivariate statistics a little bit more, we're going to have more than one dependent variable. Right, so if we have more than one dependent variable, like we had y and maybe we had like w, I don't know, I'm running out of predictors. There will be another error that goes with every dependent variable we have. And when we have more than one error, we're going to have more than one error variance. And possibly we may have covariances between them. Remember what covariance was from the last time? It's like variance with a scale. So the model for the variance really comes into play in multivariate models because very quickly we can have lots and lots of terms that are needed to fill up that covariance matrix. And we may put in some type of limiting model to make it easier to do. But later on we'll talk about that. So up to today, you may not have heard up till this class, you may not have heard it described as a model for the variance, but it will be increasingly important in multivariate statistics. And there's only one parameter, and that's usually why it's not described as a model. It's this: the parameter is the residual variance. That's all there is. But today we're going to focus on fixed effects. How are we doing? Questions? All right. So from now on, we're going to think carefully about exactly how the predictor variables are entered into the model for the means, or by which a predicted outcome is created for each person. Why don't people always care about the scale of the predictors? So in this case, scale meaning what's the center point? What's the variance? So a lot of times, in particular when you're taking most intro-level regression and ANOVA classes, we don't talk about the scale or the center point because it doesn't affect the amount of outcome variance we explain by putting it in the model. Right? You plug in x, you get a certain r squared. If you plug in x minus its mean, you get the same r squared. So why do we talk about it? It doesn't really matter. Well, it does not affect the outcomes predicted by the model itself because all the parameters that might shift still give you the same predicted value. So a lot of times we just ignore it. We don't think about it. Particularly us stat people, we're kind of like, whatever, it's easy, just throw it together. But why should it matter to us? Number one, the intercept represents the expected value when x equals 0. So we can always come up with nonsense values for the intercept if x equals 0 isn't in the data. We saw that last week, or 2 weeks ago. We had a person that was no inches tall had a predicted weight that was negative 224, right? So that was not good. The other big deal is that the bigger deal is not just the intercept, which we're going to see today, it's the interaction that it involves as well. The interaction of a parameter, if you talk about a main effect, you have variable x and z here. Oops. Right? So x, this is the main effect of x, this is the main effect of z. Both of those are conditional on the term that interacts with them being 0. Right? So x1 is the increase in y when x goes up 1 unit, conditional on z being equal to 0. So that becomes the big picture to me as to why we really matter. We need to know what 0 is to better describe what our main effects mean in the presence of the interaction itself. It also becomes even more of a big deal when we have more complicated models such as multi-level models, where we have to put random terms here. We have, like, the multi-level model is an example where we have like students nested within a classroom, where we have observations nested within a person over time. Those models, some of the variables in there we may allow to be what we call random. Helps to take care of the dependency that might be induced by the group. But what we set to be random also depends on whether or not the thing it's multiplying, or the variable it goes with, what 0 happens to be. That matters what 0 is there. So that'll be a big deal too. So for continuous predictors, we saw this last time. It's really easy to make the intercept important or interpretable because we can center it. All right? Actually, for any predictor we can center. For quantitative predictors, though, it makes it especially easy because the center point, we could either center it by subtracting a constant, right?